So now we want to talk about phase and frequency modulation, and just want to point out in the most general form we can write an RF signal as cosine of phi of t, and phi of t is called the total phase, and it can have a time varying frequency and it can have a time varying phase. And initially this is a little bit of a hard concept because normally we think about phase as cosine of omega t plus phi, and we think about, that's our phase. But in reality, all of this is our phase, because remember, a cosine is just looking for some number to put in here, right? It doesn't care what it is. And so this is the argument of cosine. It's just that conveniently over time we've split these up into a time varying one, into one based on omega and one based on phi. One depends upon time and one doesn't, but both could depend upon time. And if this is your phase, then what's frequency? I thought this omega was frequency. Well, we generally define the instantaneous frequency as d phi dt. And I'll just do a quick example so you feel comfortable with that. Cosine of 2 pi ft plus pi over 2. If I asked you what the frequency of that was, you'd say, it's f, right? Well, according to this, we take phi and we take the time rate of change of that. So d dt of 2 pi ft plus pi over 2 equals f, right? Actually equals 2 pi, right? And so you can see right away that this is consistent with everything you've known before. It's just easier to talk about this phi of t, and the reason we do is that when we talk about modulation, we're really talking about just modulating phi of t, whether we do it by changing the frequency or changing a static phase, if you will, is just a matter of semantics, because mathematically we're just looking at changing phi of t. And so phase modulation we can think about as a fixed frequency, we modulate the phase, or frequency modulation can just be written as the time integral of our phase change, or we could actually have omega c change. But this changing with time is equivalent to having omega c change with time, because it's all about phi of t. All right, so that's a little bit of mathematics about phase and frequency modulation, and here's just an example of an FM/PM waveform. Sometimes it's really hard to tell whether it's frequency or phase modulated, and the reason is because there is no difference, right? We're just changing that argument of cosine and sine. A couple comments. Typically in phase and frequency modulation, the amplitude is constant, which makes the signal immune to noise, which is good. The data is usually contained in the zero crossing intervals, and one bad part is that typically phase and frequency modulation, because remember it's cosine of phi of t, right? Or we're modulating phi of t. Well, this is a nonlinear function, therefore our bandwidth tends to be very large. All right.